Hi guys, welcome back to Affordable Chemical Engineering Tools, and today we want to continue our CSTR demo in Excel. Excuse me. So in the last video we already talked about our equilibrium constants, and we have made it a function of the temperature, so not too much of an issue now, right? So so we have to continue if you want to finish our reaction kinetics. So we've already have our mixture thermodynamics and equilibrium. Let's move on to a little more about the kinetics. So to make it easier let's just copy and paste these things over so that we have a good reference towards the bottom, and this we can shift to the side. Or maybe we can, like paste it back on the first page, whichever is more convenient. So let's just put our data here. Yeah. So 1, 2, 3, 4. Let's move it up where it should be. It's over here. Alright. Just press the saving button. I'll just do a saving button. I always have the habit of saving every now and then. Just pressing Ctrl S on Windows so that I won't lose any changes I've made to this file. Okay. So yeah, let's get on with kinetics. So what's in the kinetics part? Now we have the K1 and K2 as well as the adsorption equilibrium constants. You can take a look at the notation here. It says equilibrium adsorption constant, which is this big KH2, KCO2. It describes the equilibrium between CO2 each of the gases in the gaseous state, and the equilibrium between that and the adsorbed state, which is the CO2 which is stuck or so-called weakly absorbed on the surface of the catalyst. So that's what this is actually describing. Okay, so let's just key these things in along with the rate constants here. So the first one will be for the CO2 hydrogenation, the second one will be for the reverse water gas shift reaction, or the water gas shift reaction. Yep. And let us begin. Oh, okay. Okay. I just realized something. You can take a look at these. Yep. Take a look at these and see if you can find any difference. You see, sometimes what is being presented, you can see here that the reactions are somewhat in reverse order. Can you see the second reaction here? So CO plus H2O reversed, it becomes CO2 and H2. So yeah, these two reactions are exactly in the opposite direction, so we'll have to take note about these things later. But regardless, we'll still have to key in the kinetic constants. So anyway, moving on, let's just talk about K1, K2, KH2, KCO2. Yeah. The KP1 and KP2 are, whatever is over here. And KH2, KCO2, methanol, K water, and KCO. So let's just put that in first. KH2O, KCO. Alright, so anyway, with this new data, is there anything we need to change about the equilibrium thing? Well, this actually talks about CO in the reverse. So that this actually talks about CO2 going to CO, and this is where this is the direction of the reaction. So we should sort of look out. Yeah. So in this part, it should affect this one, the RWGS reaction. So it says -2073 over the temperature plus 2.029, and that specifically is for the reaction from CO2 to CO. But here is from CO to CO2. So this is not Kp2, this is actually 1 over Kp2. Alright, so yeah, that's the only change we have to kind of make. So yeah, so this is Kp1, this is log 10 of Kp1, this is Kp2, this is log 10 of Kp2. I'll just name this as the constant, and this is log 10 of the constant, just for the clarity. Yep. So okay, if you're not clear what I've done, basically what I've done is, okay, I've noticed a small discrepancy between the water gas shift reactions. So one is exactly the opposite of the other, and that means the equilibrium is kind of opposite. It's the opposite of the other. So if you have any questions, you can post it in the comments. I can explain to you a little more. But yeah, if you study equilibrium, this should be quite clear to you that opposite, having the reactions in the opposite direction, it means that the direction is kind of opposite. Yeah. So anyway, let's just save this. Let's just save this and continue. Right. Anyway, K1. K1 is 3E9. So let's just put 3E9 at the start. 3E9 and 25 kcals per mole. Let's just remove this aside. 25 kcals per mole, or 104.7 kilojoules per mole. Let's just put the raw numbers there. So I'm just going to say this is the kmol per kg cat per hour. Or let me put the units here. Constants and units. I'll just put it on top. Kmol per kg cat per hour. I just use a dot to represent this dot here. I use the dots here, this dot to represent this dot here, which is just a multiplication. Okay, so let's continue. 2.5 E9, 104.7. Next one, 0.14, 10 to the minus 8, 75.4, 0.44 E minus 8, again 75.4, 5.4, next is 0.11 E minus 9, and then it goes to 293, 29.3, 0.35 E minus 8, 0.35 E minus 8, and next one 75.4. So the last two are 75.4. I'll just copy this over and paste here. The KCO last one will be 0.5 E minus 10. You can see the last one, 0.5 E minus 10, 0.5 E minus 10. And Excel will just compute the rest for you. All these will be in per atmosphere. So I'll just copy this and paste it. Now, Okay, let me show you another trick. So I don't use the mouse a lot in Excel to speed things up. I will try to use the keyboard. So again, I'm using the arrow keys to move around this box, this green box you see on the screen. So to copy, I use Ctrl C, and if I want to paste over the next 4 cells, I move it to the right, and I press Shift. I hold Shift now, and while holding Shift, I press the arrow keys, and this will help to select the boxes as shown here. And I press Ctrl V to paste. I press Enter to kind of cancel away the copying function. So yeah. Anyway, this is what it should look like now. Now we have all the constants locked down, and we have this. We have the KP1 and 1 over KP2 here. Okay, so now moving on, we want to construct these equations, but first of all, we kind of need to convert the KP1 and KP2 values. So let's convert them to to atmosphere units. So to do that, we have to find out what units these things are in the first place. So when we look at this is the 30661. Let's look at the 30661, which is log K3. This is in bar 1 over bar squared. So this is in, okay, let me put the original units, 1 over bar squared. And what about the other one? The other one is here, 2073 2.029. This is dimensionless. So no problem there. We have, it looks like, yeah, we have a good thing here going on. Yeah, we have a good thing going on here. So that goes to show that we don't need to do any kind of unit conversion for this. We need to do unit conversion for this. So new, let's do a new units. We want the second one will be dimensionless, but this I want it to 1 over ATM squared. So what is the conversion from bar to atmosphere? Let's take a look. So 1 atmosphere is 1.01325. So I just type this in the Google. I'll just type this in Google, and Google will just convert it for you. So no problem there. So 1 atmosphere is equals to bar. This is the atmosphere. It's a conversion table. Conversion. So 1 atmosphere squared this is bar squared. So 1 squared is still 1, and then we'll just square this. Okay. This should be 1 over atmosphere squared. And yeah, so 1 over 1 bar squared over the bar squared. Now to do, let's say we have the numerator here, denominator. Okay, so let's just say I'm trying to I'm trying to do some fractions here, so let me use draw border, and let me use a thick line. So 1 over bar squared. So yeah, I'm using this to illustrate the unit conversion. So I'm going to do it really carefully. So this X is for the times, or rather I can just put this times So I want to convert it into a 1 over atmosphere squared, right? So let me draw that border here again. Okay. So I need to convert it this way. I need the bar square on top and the atmosphere squared at the bottom. So I'll just put the equal sign here. Let me put it at the bottom as well. And yeah, so doing that. Oh yeah, never mind. Doing that, so 1 bar squared is this much. So let me copy. Now paste it here. Of course, when I do that, you'll just copy the formulas over. However, if I just want to paste value, I press Ctrl again. And when I want to look for values, they say values. You can either click this or you can just press V. So I'm going to press V, and there, the values are pasted down. So there you go. This is the unit conversion. So bar square. So 1 bar square to the atmosphere square, you just have to multiply by this much. Okay, so moving on, it will be equals to this value times 1.02226676. That will be the new value that I'm looking for. So I'm going to paste here, Ctrl V, and that's the value in atmosphere units. So bar units. So this is the one I'm looking for, so I'm just going to highlight it in green. Okay, and for neatness sake, I'm just going to box everything up here. Thick outside borders. I like to keep things neat, yeah? So now this is an atmosphere squared. This is an atmospheric unit. And yeah, this is already based on the temperature. Okay. So now let me do some of the value calculations here as well. And I don't have to, copy the formula. I can copy the formula. I don't have to. Well, I only have to type the formula once. Then I can just copy over the whole thing, right? So K0 times exponential negative E divided by. Okay, let's put the R over here. R times T. So I'm going to close. There you go. Again, let's put the R here. 8.314. Okay, so let's do, before we continue, let's do a unit check. Over here, it says in kilojoules per mole, but R is 8.314 J per mole per Kelvin. So again, we need to do some unit conversion. So instead of instead of rewriting all the numbers, all I have to do is E in J per mole, and this one is in kilojoule per mole. Yeah, so what I have to do is just times 1000, because 1 joule is 1000 joules is 1 kilojoule. So I'm just going to drag it across to convert it to SI units. And not only that, I'm just going to shift the box here. So originally I was this was a pre-exponential factor, which I don't change. This was the activation energy value in kJ per mole, but now I want to change it to joules per mole per Kelvin, or joules per mole rather, joules per mole. So I'm going to shift it down. So all I have to do is use the mouse to shift it down, and this is still the temperature. I'm going to press OK. So I just want to shift this formula for K1 and K2. I'm going to drag it across, and I'm going to find out I have a problem. Why? I may have dragged it across correctly and the formula stays, and I have shifted it, I've gotten the correct formula. I'm getting this pre-exponential factor and this activation energy. But you see, when I shift this thing over, the T and R are in the wrong places. So what do I do to avoid this problem? Well, there are two ways. One, I can shift the boxes back manually, and well, that solves the problem. However, if I keep wanting to copy the formulas here, then I'll keep having the same problem. What I can do is I can lock the cells. By locking, I mean using the dollar signs, as shown on your screen. So this refers to cell C4, which is the R cell, and this is the T cell. So by putting dollar signs here, I'm actually locking the cells C and 4, and I can do the same for the temperature. So you can see for the cells I locked, I have basically gotten the same formula. I'm getting the data from the same cell. However, for the cells I did not lock, all the cells are shifting. So I can do all this throughout the whole thing. I get this result. Okay, I'm just showing you the example, not saying it's correct. So now let's move on to the other case, the other K values. Let's move on to the other K values here. Sorry. Yeah, the other K values. So this adsorption constants will be in delta H by RT. There's no minus sign. So what I can do is I can just drag things here to copy most of the formulas, seeing how well the formulas are extremely similar. However, what I can do is I just erase the minus sign here. I'll take it out, and I'll have this value, and I'll drag it all over here, and there you go. I have my values. Okay, so these are kind of almost the final values I want to get. So this is in kmol per kg cat per hour still, because I didn't change the units at the pre-exponential factor. I only changed the units of the activation energy, which I do want to, so to make sure the exponential factors are correct. So now I want to change maybe these units, right? These units are in kmol per kg cat per hour. Maybe I want it in seconds, so let's have new units. So kmol per kg cat per second, or it's either it's kmol per kg of catalyst per second, or mole of reactant per gram of catalyst per second. So it's about the same thing. So these two I want to change. These ones I don't have to change as long as my pressure units are in atmosphere. So let's put our values in here. So if I do this much activity per hour, how much activity will I have per second? I will just take this value, divide by 3600. That will give me a per second basis for both of these, and I will just for the rest I don't change anything, so I'm just going to put the equal sign down there and get everything like that. So for the last row, these are the values I want. I'm going to highlight them in green again, and I'm going to get my values right. And so moving on, yeah, I need a place. I want to start computing my rate of reaction, right? However, I don't have any kind of partial pressures or anything like that yet, so I will need to have a place where I can put the compositions together. So an ideal place is to get all the compositions you want to make it neat, right? So you want to have a clear place where you do the inputs, which is the temperature, pressure, and all the compositions, and a place where there is a decent place where you can put the outputs, right? So let's see whether I want to shift this box down here, but let's see whether it affects my values. So good news is that no, the values are not affected, and that's good news because I don't have to change any of my formulas. Alright, so besides that, let's continue putting in our values or mole fractions. So these are mole fraction. Let's put our mole fraction in this area, the one I'm highlighting. So put mole fractions here. So I want YH2, that's the mole fraction of H2, YCO2, Y methanol, Y water, YCO. Excuse me. So let's just give a roughly equal value for all of them. I'm just going to copy and paste here, and that will be the mole fractions, right? Or rather, let me box this whole thing up. Okay, so these are my inputs. I'm going to give them a kind of a different color. Let's give it what color should we give it? We give it a very light blue, and we give it some borders. Okay, oh, that's a bit too thick. Sorry, let me redo the bordering. Take outside borders. So to format, I want to give it the paint, fill the color. Whatever. Alright, I'll just leave it as that. And I'm going to border this thing up. Okay, it looks a bit ugly, but maybe I'll deal with it later. So anyway, line style, let's see. Draw border grid. There you go. There you go. That's much better. Okay, so what I did is basically I chose to draw the border grid, and this is what happens. So, okay, let me revise the step again one more time. So it goes to borders. I go to the drop down table. I select draw border grid, and I click it, and I do this. So to undo, I Ctrl Z, and that is done. Okay, so now that the borders are settled, I can start doing my reaction rates. Okay, so before we continue, I want to introduce you to something called sum product. Sum product. This is a formula called sum product. And why do we want sum product? Well, we can see that we're going to have lots of multiplications: KH2, PH2, KCO2, PCO2, KCH3OH, PCH3OH. So all of that is going to be very, 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 how do I put it? It's going to be very troublesome, because you're going to have to put this times the pressure, and then you're going to have to times the KH2. So that's the first denominator term. So if I'm going to do it for all of it, it's going to be very long. So what sum product does, let's say I have two arrays of 1 and 2s. So instead of equals, instead of multiplying this, instead instead of multiplying this and this, and then you just type it, you have to copy and paste it individually. It doesn't make sense at all. And then you want to still sum it up. That's not very convenient. The easier way is to use the sum product and to take this array 1 and to take this array 2, close it, and you do basically the same thing. It will have this, it will do a product of these two, and do a product of these two, and do a product of these two, and excuse me, and it's going to sum it all up in this column or this cell. Okay, so no issue there. So that's some product for you. The question, of course, you may ask is, does it work in, if the cells are kind of diagonal? Because these are in the horizontal position, these are in vertical. So let's see whether it works. Some product of this array and this array. So of course it doesn't work here. No problem. So what we can do instead, let's have a mini calculation table. So let's calculate the denominator first. So this is the denominator I'm trying to calculate. So this is the H2 part, CO2, CH3OH, H2O, CO, right? Okay, so let's have the partial pressure and of course the sum and the adsorption constants, yeah? Adsorption constants. Okay, so partial pressure, let's say this is a 50 bar. So that is just this mole fraction times this, and of course the yi and p has to be multiplied, and still we got to log the first cell as per normal. So when I drag it down, it's going to be as such. You see, when I press F2, it's going to show me the contents of the cell. Yeah. So what I'm doing is I'm using the arrow keys and I'm pressing F2, which is the same as double clicking on the cell. So F2 is a double click on the cell. Okay, so let me box up the things again, and let's do the adsorption constant. This one has to be a little manual, but don't worry, it only has to be done once. So equals the KH2, this is equals to KCO2, this is equals to KCH3OH, second last KH2O, last one KCO. So again we can do a sum product. Oopsie, sum product. So I'm going to double click this. So first array is going to be here, second array is going to be here. Close. And that is the value of the denominator before I cube it or square it. So let's box it here again, just for the neatness. So this is denominator, not squared. So I'm just going to name it funny names, like for our convenience. But of course, if other people are reading this spreadsheet without the knowledge of how it's created, it'll be quite confusing. So we can do something about it later. But anyway, we can do the denominator for R1 first, which is the CO2 conversion, the CO2 hydrogenation denominator. So it is this unsquared denominator to the power of 3, and the water gas shift reaction denominator it will be equal to this whole bunch divided by to the power of 2. Okay, I forgot one thing. There's one term at the bottom here, so by right I'll need to add 1 to this. But it kind of doesn't make too much difference in this scenario. But let's just put it for correctness sake. And with that, we are almost done. We have done the denominator part. Now we need to do the numerator, which is this batch over here. This whole lot. Okay, so let's continue with the numerator. So I'm just going to box this up again. Now I'm going to put for numerator calculation. So again, I'm going to copy all of this. Do I need to do that? No, I don't need to do that. So okay, we're going to have this term, this term, this term, and this term. So let's put CO2 hydrogenation. I need the K1, the small K1, times KH2 squared times KCO2. So let's get exactly that. So let's have K1, the K1 value, which is this, times KH2 squared. KH2 squared. So K1 times KH2 squared times KCO2 times KCO2, which is this. There you go. Now we want this second term, which is pH2 squared PCO2. Okay. So pH2, partial pressure of H2 squared times PCO2, which is this. I'm not going to drag anything, so I'm not going to drag the cells down like this or anything. So I'm not going to do like I'm not going to log cells because I think it's unnecessary at this juncture. So we need a 1 over Kp1 value, 1 over Kp1, which conveniently we do have at here, 1 over Kp1. Oh, this is Kp1, so we need to invert this. So this is what we have. I'm going to bold this. So this is what we have, and the last one will be this very messy thing down here. P methanol times P water divided by pH2 close to P methanol times P water divided by pH2. So let's just have the result at the bottom. I have a numerator. So let's just copy exactly what we have here. So I have the KH1 and whatnot, and then you have the bracket, then you have the pH2 term here, whatever this is. So you have that, and you have to do minus this times this. Okay, so it's the 1 over Kp1 times the P, CH3OH, pH2, and the pH2O. All that together, that will give you the numerator. Yep. And for water gas shift, again we have similar things, so I can copy most of it around and just make the modification. So here is K2, so this is K2, and I have KH2, and then I have KCO2. Okay, what's next? Anyway, what's next? pH2 PCO2. pH2 times PCO2. That's pH2 and PCO2, and 1 over Kb2, and the last one will be PCO times pH2O. Okay, so again, let's do some multiplication. K2, and you have KH2 times KCO2. Alright, that's the first thing. So the other one is that you have pH2 and PCO2. So where is pH2? pH2 and times PCO2. And 1 over Kb2 is just nice. It has been inverted for us. This much. And the last one is PCO times PH2O. So now we have a very neat looking spreadsheet. And it just so happens that the form of the formula is very similar to the first CO2 hydrogenation CO2 hydrogenation reaction. So you can see this, then you multiply into the brackets of this times minus this times this. It's a very similar formula, form, and that's what we conveniently just keyed into Excel. So let's put it here. Copy and paste. So this, which is this outside term, this is the first term here, this is the second term here, and this is the last term. Just want to be checked and be extra careful. And last but not least, we need our reaction rates. So mole per gram cat per second, and that will be equal the numerator of the CO2 hydrogenation divided by the denominator, enter, and for the water gas shift, numerator over denominator, and press enter. And that is it. That is it, guys. Thanks for watching. Yeah, pretty much that's all you have to know. For this round, you're just going to input the kinetics into the Excel spreadsheet, and yeah, I'll see you guys next time to do the mass balance of the reactor. Thanks for watching. I'll see you in the next video. Bye.